Problem 11 on our WebAssign assignment for 4.5 is based on number 25 out of the text in the same lesson. And we're given this situation where we're going to lay some cable both underwater and on land, and we want to minimize the cost. I'll quickly read through this with you and then let you know how I'm going to set this thing up so that we can use our derivatives to help us find this optimum location for point P. In the following diagram, S represents the position of a power relay station located on a straight coast, and E shows the location of a marine biology experimental station on an island. You can see S right here and E right here. A cable is to be laid connecting the relay station with the experimental station. If the cost of running the cable on land is $1.50 per running foot, and the cost for running cable underwater is $2.50 per running foot, locate the point P, which is this point here. That will result in a minimum cost. In other words, we're solving for X, which is this distance right here. Everything in our problem is going to be based on X. Now this description of the problem gives us a hint as to what we need to do. We need to minimize cost, and you know we usually write cost as C of X, right? The question is, how in the world do we figure out how much it's going to cost? And for that, we need to use a little bit of prior knowledge here. To figure out cost, you need to know the number of feet times the price per foot. So we usually call that distance times the unit price. And I'm just going to write it as feet times price. And so we need to know the feet or distance times price on land plus the feet or distance times price for underwater. Now the land part is pretty easy. We know that our measurement for land is 10,000 minus X. 10,000 feet minus wherever we locate P, that's going to be our distance on land. And to figure out the price, we'll simply multiply that by $1.50 per foot. The part that's difficult to identify is, what is the distance underwater? What is this distance right here? That blue line. Well, for that you got to think back to geometry class, and we had a famous theorem called the Pythagorean theorem, which had to do with the measurements of the legs and hypotenuse of right triangles. So we have a right triangle here, and the two legs are 3,000 feet and X feet. So we can use the Pythagorean theorem to figure out the distance on that blue diagonal, which is where our cable will run underwater. The distance there is going to be the square root of X squared plus 3,000 squared. And then, of course, we want to multiply that by the price underwater, which is $2.50. So with these two pieces put together, we're going to have our cost function. We're going to have $2.50 times the square root of X squared plus 3,000 squared plus $1.50 times 10,000 minus X. That's our cost function. And from there we can do our calculus, which is we get the derivative, we find that critical point, which should be our minimum, and then we'll know where to locate point P, because point P is just located at whatever our X value is down here. So let's go set up that cost function, take the derivative, and find out where X is. So you can see I've written out the cost function, and actually what I'm going to do here is remind you that this 250 square root of X squared plus 3,000 squared probably is going to need to be written like this with a power, so that we can use our power rule. And yes, I'm being lazy. I haven't calculated what 3,000 squared is yet. But anyway, let's go ahead and do our derivative. You know what? On second thought, let's go ahead and distribute this also. So this would be 15,000 minus 1.5x. Then we can take our derivative fairly easy here. So C prime, the derivative of the cost function, we're going to use the chain rule, the general power rule. Bring this 1/2 down and multiply it by the 250, and then make that a minus 1/2. And then don't forget the chain rule, we have to multiply by 2x. So this is going to be 1.25, because half of 250 is 1.25, times x squared plus 3,000 squared to the negative 1/2 times 2x, because of the chain rule, plus 0 for this, derivative of 15,000, 0, and then minus, so I'm going to get rid of that plus sign because I don't need the 0, minus 1.5, or 1.50, because the derivative of negative 1.5x is negative 1.5. Okay, so we have this crazy looking algebraic expression for the derivative. Let's try and clean this up so we can do a little bit of math with it. I have a 1.25 and a 2x here, and that'll multiply together to make 2.5x. And then this is a negative 1/2 power, so that means that that square root gets moved to the bottom, and so we have the square root of x squared plus 3,000 squared underneath that 2.5x. And we still have the minus 1.5. Okay, now that we have this derivative, our job is to set it equal to 0. So let me just go ahead and put a 0 right here. And then we're going to use a little bit of creative algebra. We can add this 1.5 to the other side, and we can multiply by this square root, so that we end up with 1.5 square root of x squared plus 3,000 squared equals 2.5x. And because that radical's there, the only way we're going to be able to get anything done here is if we square both sides. And we have to be careful when we do that. When you square both sides, you get 2.25, because that's 1.5 squared, times x squared plus 3,000 squared equals 6.25x squared. Distributing the 2.25 gives us, and finally now I had to go ahead and multiply this out. This is 20,250,000. I hope my math was right on that. And that equals 6.25x squared. And on the next screen I'm going to continue, but just so you know, I'm going to subtract 2.25x squared from both sides, and that'll make this a 4x squared. So we're going to have 4x squared equals 20,250,000, one more 0, dividing by 4, that's going to be 5 million and change. That's 5 million. Oh, shoot, I had the wrong button here. 5,062,050. 62,500. How's that sound? And then we're going to take the square root of that, and believe it or not, we get a nice answer, which is 2,250 feet. And so this is going to be the location of our point P, where the cable will go from the land through the water to the island. That's going to be our minimum cost right there. So that's how you locate that X point. I know the algebra on this problem was a little more complicated than some of the polynomials we've done, but this is showing us how we can apply these derivatives and solve some more interesting problems. Feel free to post post questions on the discussion board if you have any. Good luck.